We're going to briefly talk about how we represent these fields before we go a little more into detail about the electric field from a point charge. So when we're drawing our fields, this here is going to be our source, and this black dot here represents a position in space. It doesn't necessarily mean that there's a charge there. It's just a point in space, and we've drawn the electric field vector. So something to note is that the electric field vector is not an arrow connecting two things. When we first met vectors in mechanics, we talked about the fact that vectors have a magnitude and a direction. So this electric field vector is actually describing what is happening at that point. At this point, the electric field points in this direction and is that strong. So we might want to think about what's happening at other points in space. So I've drawn some black dots representing other points in space, and we want to think about what the electric field is going to look like there. Now, I haven't actually defined yet what the electric field does actually look like from a point charge. We'll do that in the next video. So I'm going to sketch this out really quick, but again, I want you to think about the fact that we're describing it at these points. We have to then get the magnitude correct and the direction correct. Now, drawing it by hand, I might not have done that good of a job, but note that these vectors point in different directions and they're different sizes. So what we're going to learn about the electric field from a point charge is that it's larger the closer you are to the charge. So this point in space is the closest, so it has the greatest magnitude. The second thing that's true is that it always points directly away from the charge, which I've tried to do. So this point here is a similar distance, so it's almost the same size. It's a little shorter since it's slightly farther away, but it points a little bit into a different direction since it's at a slightly different position. So that's the main idea. Again, make sure that you don't think that you're connecting two points. You're just representing the electric field at each of these points as a vector. So these figures from the book will be a little more clear. Note again that the electric field is defined at every point in between these. These are just the points that we've happened to choose in space. Note that there is a pattern to these points, and it lets you see what's happening with the field. Again, the closest points have the largest fields, and the farthest points have the smallest fields. And that in each case, they point directly away when it's positive. When it's negative, they actually point towards the charge. So the field is still on a line between this point in space and the charge, but positive is away, negative is towards. Note that the strength is still the same though. So if these are the same magnitude of charge, the magnitude of the field is the same. However, the direction is a little bit different. So I hope that this helps clarify a little bit. The book calls these field diagrams, and it's important to note that this might be different than the representation you've seen of fields in the past. There's also what are called field lines, which we will be using occasionally, but these field diagrams or field vector diagrams are actually much more helpful for what we're trying to do. So please work with trying to generate, draw, and understand and interpret these field vector diagrams since they're going to be our primary representation, but you will also see the field line representations, and we'll talk about that in the next chapter.